So let's get trucking. Where we left this guy off, it should show our last, or output queue rather. And I think that guy looked correct. Let me go ahead and open up Keynote here. That way we could type in the same example that we had. All right, so if we do 8 divided by 2 times 3 plus 7, 8 divided by 2 times 3 plus 7. Oh. Say this again? Oh, I had copied it, is what you're saying.
No, it was on the layout. You set the text to that value.
Oh, as a starting point. I get what you're saying. Okay, so this should be 8-2 divide 3 times 7 plus. 8-2 divide 3 times 7 plus. Okay, so that's giving us an accurate output queue. So now we need to actually do the math for this guy. We're going to feed off of the queue. So we'll feed the 8 into a number, the 2 into the number, then we hit an operator, so we do math. So we do the math between these two, put the result back into one of our numbers, read in another number, so on and so forth. All right, so here's our process output queue. And then I'm also, did we write a do math already? We did not. So I'm also going to give myself a little private function above here. And this guy will return an int. Call this do math, and we'll say int num1, int num2, char op. All right, so we'll ask the question, if op is equal to plus, and then return num1 plus num2. Else if op is equal to minus. Now, we're making a decision here of which number is minus the other number, so we need to make sure we pass it in the right order. So we'll return num1 minus num2. Oh, thank you. Else if op is equivalent to multiplication, return num1 times num2. Else it must be, because we're only supporting plus minus divide times, right? We'll do return num1 divide num2. All right, so that's our do math. We'll call that whenever we run into an operator. Okay, so now to process our output queue, we want to keep feeding off the front of the queue, so we want to keep dequeuing it. And let's look at our queue. And do we have a is empty or something like that? Yep. So we have an is empty that tells us when the queue finally is out of stuff. And then we'll call dequeue, and dequeue is going to give us something of type node. And then we can ask which kind of node are we looking at. Where am I? This guy here. So we'll say while this dot output queue, while that guy is not empty, we're going to do some stuff. Let's go ahead and let's just give ourselves a temporary node, node temp. And then we'll say temp is equal to this dot output queue dot dequeue. Okay. Now we need to ask ourselves which whether we're looking at an operator. If we're looking at an operator, so if temp is an instance of what do we call these op node? If it's an instance of op node, then we're going to do some mathy stuff. Else, we need to fill in some numbers. So what I'm going to do here is we're going to have a couple of numbers. So we're going to have int num1, int num2. Now we're only going to fill in num1 the very first time. So I'm going to create a little Boolean. Let's just call this guy flag. Well, call it fill num1. We'll say is equal to true. All right, so if I'm in this else, that means I definitely have a number if fill num1, so if that guy is true, then we want to go ahead and say num1 is equal to didn't write the generic version of that, that's fine. So we'll turn this guy into a num node temp dot get payload. So that'll get us the numeric version of num1. And then we'll go ahead and say fill num1 is equal to false. So we don't do that again. Else, we'll always fill num2. with the payload of temp. Okay. Say this again. No. Yeah, you'll see how I'm approaching this. Because I only ever want to fill that once. This way. Otherwise, I'm always going to put my answer back into that guy. All right. So, and I'll actually show that on the keynote here in a second, just so you see the thing I'm doing. Otherwise, what I'm going to say here, if I'm dealing with an op node, I'm going to go ahead and I'm going to say num1 is equal to the result of this dot do math, passing it the current version of num1, the current version of num2, and then my operator. My operator is the op node version of temp dot get payload. Aren't these guys ints? Oh, it thinks it might not have a value. We happen to know that we will have put a value in here by now, but Java wants us to make sure those guys have numbers in them. Okay, so that will refill num1 with those values. So now let me show you what's actually happening here. I'm going to steal our output queue thing here. Process output queue. All right, so that guy looks like that. We have a num1, we have a num2, and these guys are starting off being equal to 0, so we'll just show how it currently works. All right, very first thing we do is we dequeue the 8. Is that guy an operator? It's not. I'll go ahead and give myself my variable here. What is it called? Fill num1 is equal to true. So I dequeue the 8. Is 8 an operator? No. So I need to, must be a number, so I need to fill it into one of my things. Since fill num1 is currently equal to true, I'll put that guy in num1. I'll flip this guy to false. Then I'll dequeue the next one too. Is that an operator? Nope. So fill num1 is false. So I'll put this guy in num2. I'll dequeue the next thing, divide. Is that guy a operator? It is. So what will I do? I'm going to do some math. I just real quick want to look at something here. Yeah. So I'm going to do the num1 divided by num2 is the correct order. So I'm going to do some math. What's the math I'm going to do? I'm going to do divide num1. Well, I'm going to do math, passing it num1, which is 8, passing it num2, which is 2. I'll do the math for divide. That should give me a 4. The result, so what I'm saying in the code is I'm saying num1 is equal to do math of num1, num2, and my divide. That's what I'm effectively passing in. So I'm overwriting num1 with my 4, the result of that division. Okay? Then I'm going to continue on. I read in my 3, not an operator, so we immediately put it into num2 because fill num1 is currently false. So I'll put my 3 here. Then I DQ again, I get my multiplication. Multiplication says, I need to do some math, so I'm going to do math, num1, num2, and multiplication. Storing the result in num1, so 4 times 3 is 12. Storing the result in num1. Then I DQ the 7. Not an operator, so I put it into my numbers. Fill num1 is still false, so I fill it into num2. DQ again. Here's my plus. Is that an operator? It is. So num1 plus num2. I'll do the math, storing the result back in num1, which is 19. Now my queue is empty, correct? And my final answer is what's currently stored inside of num1. See how that's working? So when this guy is all said and done here, when this while loop is done, I should be able to do a system.out.println final answer colon num1. All right, so that's process output queue. Now let's go down here to the click me button. So this was just outputting our test queue thing. So we did processor input queue, which should fill up the output queue. Then finally, we'll say this dot process output queue, which should ultimately display our final answer. All right, and our final answer for this guy. Oh, hold on, I did something very funky there, didn't I? It's not the right answer. Did I not do my multiplication? Back up. 8, 2, do math 4, 3, then multiply the 3 times 4, giving me the 12. No, that's right. Did we do the math wrong here? 8 divided by 2 is 4. 4 times 3 is 12. Yeah, that's right. We're like. Oh, that was for different inputs? Yeah. Oh, okay. Good. All right. That seemed right. All right. So we'll just process our output queue afterwards. We'll make sure we put in the same input. Why doesn't this guy move? Shouldn't he be movable? Yeah, he doesn't seem to be movable. Oh, whatever. All right, so this is 8 divided by 2 times 3 plus 7. And there's our final answer of 19, processing the output queue. All right, so there is process output queue. Questions on that? Anybody do it substantially different? Go ahead.
Since we're dealing with ints, you know, it's 8 divided by 2, so it's like if it's like 8 divided by 3, would that screw it up?
Wouldn't screw it up. You would just do integer math. So if you wanted to change this, you would go in and update our num nodes to hold floats. or hold doubles instead, and then you would do math on doubles instead of ints. Yeah, so this does integer division. So I guess the short version is yes, it would screw it up based on what you might assume the solution would be. Did anybody do this substantially differently? I created an infinite size array and I just kept filling it up with solutions. Go ahead.
The Boolean Q number one should make sense now. Let's specify them. That's so easy.
So did you fill up num1 multiple times with other values?
It seems like it. No, actually not. I use a while loop just like that. But I use that in just the same function process output Q.
Hmm.
And, yeah, I DQ it, and every if and else I do the math and I NQ it to like a solution stack. And it seems
Okay, I gotcha. So you created a stack for your solution, and then you would anytime you had it's actually a pretty good solution. So anytime you had a number, you push it on the solution stack. Anytime you had an operator, you pop the two guys off the solution stack and did the math. Yeah, oh, that's a good one. Let's just write that real quick. So we'll call this process output Q2. Actually, that solution would be more like how I explained how to do the math, right? Yeah. I mean, this effectively does the same thing, but yeah. So let's write it that way first, or second, I guess. Output Q2. All right, so you went ahead and created you called it a solution stack?
Yeah.
All right, so we'll call this guy, do we just call it a stack, or we called it a... Well, that sucks. That's not going to help us. We need a number stack. So you just stored them as generic nodes in there?
Yeah.
And then pulled them out? All right, so this is what I'm going to do. I'm going to go ahead.
There's also solution Q. I also made solution Q.
Okay. So what I'll do here, just so we can introduce it, I'll go ahead and introduce how to use the generic stack data structure that's in Java. Since now we're past stacked, we can use the generic stack data structure, right? So I'm going to go ahead and I'm going to create a stack. And this is going to be a stack of num nodes. And this guy should be in java.util, I think. Yeah, java.util stack. That's where our built-in stack data structure is. Where's my process? I'm lost. All right, so we'll call this guy solution stack. This guy will be a new stack of num nodes, like that. So this is called generics. So I'll actually just steal this. That line won't. It'll be the wrong color. It'll be easier for just me to type it again. So the generic syntax for a stack is stack type varname equals stack type. That's the constructor for it. So this syntax there, where we have something that looks like type in Java, is something called generics. So it allowed them to create that data type, the stack data type, to hold anything that's an object. So they wrote it generically, hence generics. All right, so when I built it, so if we just, if we don't do anything special, if I just create a normal stack, that type is assumed to be object. Okay, so it's assumed to be object, which means let me show you back out here. Even though there's nothing in my stack right now, if I say solution stack dot pop, notice that the value it's returning is a num node, because I built it in terms of num node instead of a generic type. Make sense? Now, if I take this portion off and build my stack like that, and then I do dot pop, notice it's coming out as an object. So the version of stack that they wrote as part of Java stores anything that's an object. But then they've upgraded it by attaching the generic syntax to it and saying, if you want to go ahead and save yourself some time casting later, you could build this in terms of generics so that pop will automatically cast object to a num node in our case. That makes sense? So it allows you to use this thing to hold the type that you actually need it to hold, rather than storing everything incognito as an object and then having to convert it out when you bring it out. Not the end of the world, just makes the syntax a little messier because you're having to do the parentheses with the typecasting and that kind of stuff. Okay. So I'll still give myself my node temp just to grab the thing out of the output queue. So we'll say while this dot output queue is not empty, let's do some stuff. First thing we'll do is we'll say temp is equal to this dot output queue dot dequeue. So we'll go ahead and get the node from that. We'll ask ourselves if temp is an instance of op node. So if it's one of those guys, we're going to do some math. The math that we're going to do is going to be, so we're going to say solution stack. Well, let's go ahead and get our answer first. Otherwise, we'll have well, here, let me write it the long way first. Then we'll see that that maybe is a little bit aggressive. So solution stack dot push. So we're going to be pushing something onto the solution stack. What are we going to be pushing onto the solution stack? The result of this dot. Oh, actually, that's going to return an int. So I need to rewrap it as a. We'll write it because it's going to look pretty impressive. This is going to be a new num node containing the result of this dot do math of solution stack dot pop. So if when we push it on there, so I'll push the 8, then I'll push the 2, so I'm popping. So I'm actually popping off num2, then I'm popping off. Okay, so I'd have to reverse this. Let's just write it the long way first, then I'll fix it up. So we'll pretend like we're passing it in the right order. So solution stack dot pop, solution stack dot pop. Let's hide some of this stuff. And then, and that's dot get payload. Dot get payload. And then the last value we're going to pass it here is going to be temp dot get payload for our math. All right, and then so we're going to push a brand new num node built out of the result of do math on the pop of our solution stacks payload. The pop of our solution stacks payload, even though these guys are actually out of order right now. So we can go back and rewrite our do math to swap num1 and num2. That would then make them in the right order. So heck, if you actually wanted to, because that looks kind of impressive. All right, so we'll push that back on there and do our math. Else, we're going to go ahead and say solution stack dot push, and we know what we have in temp must be a num node, so we can go ahead and push that on there. It's saying this guy cannot be applied to normal nodes. Even though we know it's a num node, we have to go ahead and cast it to a num node. Now he's happy. And in the end, we can say system.out.println. Final answer solution stack dot pop dot get payload. Something like that should be our final thing. So let's run this real quick. Make sure we're calling our process output Q2 on this guy. Eight divided by 2 times 3 plus 7. Okay, and there's my final answer of 19. So that's using a stack to pull this off, which actually is probably the better answer. This other one was more shorthand just because we knew how it worked, but this is probably the better one. All right, now this line is fairly nasty looking, right? I would not encourage you to write that like that. Technically it worked, right? But we didn't need to have it that crazy. So I'm gonna go ahead and I'm gonna just switch this back to num1 and num2. And then what we'll do in here is we're gonna create a int num1, int num2. When we do the math, we're gonna go ahead and we're gonna say num2 is equal to solution stack.pop.getPayload. That'll be num2. The very first thing we pop will be num2. Num1 will be equal to solution stack.pop.getPayload. All right, then we're going to get our answer. So maybe we can actually store answer in another variable here. So we'll say answer is equal to do math of num1, num2, and then temp.getPayload. And then what we'll do is we'll push back on our stack a num node created out of answer. So this gets, the first thing on the top of the stack is actually our num2. The second thing is our num1. Get our answer based on do math. This guy's an int. Then create a new num node out of that answer and put it back on our solution stack. That would be the more correct way probably of writing it. A little bit longer hand, but also readable. Okay, so let's run that real quick.
Can you try this value, this expression for me? I don't know why
Yeah, let me test this one real quick and then we'll try your other one. Ruh-roh. What'd you do? Oh, empty stack exception. We didn't do the final math. I think I maybe didn't write the function correctly. Eight divided by 2 times 3 plus 7. Yeah. User error. I didn't type in the full. I think I probably said plus and then forgot the 7 or something. All right, so you want me to try a different expression? All right, what am I trying?
123 plus 15 times 10 divided by 90 and minus 21. I'm just trying to use all the...
Like that? Final answer is 99?
wouldn't like in the shunting yard, the reverse notation coming up as 123, then 15, then 10, then multiplication, then 90, which is doesn't.
Yeah, the multiplication goes left to right. So multiplicate.
Should, three numbers in a row. Does that sound right?
Oh, I see what you're saying. So if we're processing this, this will be 123, then it'll be 15. The plus is on the op stack. The multiplication goes on top of that. Oh. It is right and would break my first version of this.
The solution, the way you solve it.
Yeah. The num1, num2 with the Boolean
Because
would not work for this.
you know when I used for loop, I tried multiple solutions. I used for loop with three arrays, and it did not.
Yeah, the stack solution works easily for this because it's doing the math. Yeah, it doesn't matter whether you have 5 or 6 or 7 nums in a row on there. Yeah, this would break my other one. Oh, that's unfortunate. Copy. So let's switch this back to process output queue, my original. How do I force it to do the... I don't have an insert key on here. I got it to work before. Actually, let's just do this. Remute it again. 123.
Plus 15 times 10 divided by 90 minus 25.
Yeah. It didn't crash, but wrong answer. Because I overwrote num2 with the third number.
Yeah.
So the second number disappeared in my original
But
solution.
This is the correct reverse rotation, right?
Well, this is the wrong answer.
But the reverse rotation.
Yeah. The output queue was correct with 3 numbers in a row. Yeah, and it required the stack in order to solve it. So technically, my first solution was not a good solution. Would only have worked for certain inputs. This one would work for all inputs, operating off a stack. All right, so we'll show this as the better solution. This guy. All right, questions about that one? So, yeah, it's better than the solution I wrote. All right, so that is, let's say, a version of shunting yard that only works on some operators. Okay, so let me go ahead and push this final solution up. Okay. Now, I guess we could have put out on a text view or something like that, but that's overkill. Wasn't all this stuff from a different class? The stuff I have down here? Yeah. Forgot to move that back. So let's go here. So up to this point, we've been dealing with what we referred to initially as linear linked data structures, right? So we started off with this base type of, we started off with a base type of arrays. Then we looked at linked lists, which are more of a generic data type. Then we look at some specific applications of linked lists like stacks and queues. All right, fair enough. Now, we want to start looking at non-linear linked data structures. All right, so the first one that we're going to look at from this is something called a binary tree. All right, so a binary tree is it's easiest probably just to show a picture of it. So it's a guy that's going to look something like this. Just kind of stop it there, where every node has at most 2 children. So this node has 2 children, this node has 2 children, this node has 0 children. All right, but it goes farther than that. It's not just, and let me just quickly go into the book here. I want to make sure that's the next thing they introduce. I'd be very surprised if it's not with trees. I'll probably do hash tables after trees. Trees make the most sense next. Well, let's do that. So yeah, very first thing is a binary tree. I want to make sure I'm teaching it the same way that they're doing it. Yeah. Okay. So the idea with a binary tree is when we build this, so an initial binary tree is going to look like that. And let's just put numbers in here. So I'm going to put a 2. So we initially had an empty tree. So the tree had nothing. I tried to add 2 to the tree. It was an empty tree, so we added it right there to the root node of the tree. So we're going to call this guy root. Top of the tree, yep. And what you should do when you think about trees, they're like trees in real life, but they're upside down. Because the roots are in the ground in real life, where now roots are up in the... doesn't matter how you think about it, but it is representing a very weird and very specific type of tree that only ever has two leaves that you could think of a tree that has roots as just it's the root collection is the one root. Yeah, the base. But then after that, you only ever have 2 branches coming off of. So it's a very specific, type of situation. Well, we're going to look at n-ary trees as well, which is going to probably be more like a real tree. All right, so this would be the root node. Now, when we create a new node, we want to add this guy to the tree. Everything to now it is interesting. It looked like the book did, it put the stuff that's less than it on the right and the stuff that's greater than it on the left. And I usually teach it the other way around. possible they're not really talking about that order yet. Let's just see when they go in here. Yeah, they wrote it correctly here. So maybe really their first example is a little misleading if you're looking at it from a binary search tree perspective. Because typically what you'd have to the left-hand side, so this is our root node Jones. I'm teaching it with numbers because it's a little bit easier to work with initially. But everything to the left of Jones would be less than or equal to Jones. So that means these would be things that start with letters of the alphabet that come before J. But in their example here, it looks like it's the other way around, right? But in the next page where they're doing numbers, the numbers to the left are smaller, the numbers to the right are larger, and that's how I teach binary trees. So their first example was maybe just a little misleading. But they weren't talking about the order at that point. They were just showing what the tree looked like. All right, so we have our root node 2. Now we try to add this next guy. So this next guy drops into the top of the tree. We don't have room for him at the root. So now what we're going to do is we're going to say, is this guy less than or equal to 2, or is he greater than 2? Since he's greater than 2, we're going to place him on the, well, we're going to try to place him to the right of this. Since there's currently an available spot there, we'll drop it. So this guy now becomes the right child of 2. Let's say I want to add another 4. Is 4 greater than or equal to 2? Or is it less than or equal to 2, or is it greater than 2? It's greater than 2. So we'll add to this side. Is 4 less than or equal to 4, or is it greater than 4? It's less than or equal to, so we're going to add it to the left-hand side of this guy. There's room, so we'll go ahead and drop it. I want to add another 2. Is 2 less than or equal to 2? It is. So we place this guy here. So binary trees get a little difficult to draw if you get too many leaves, because then they start crowding into each other and that kind of stuff. So they're kind of tough to create a representation, a visual representation for it with boxes, at least. Okay, but we get the general pattern. Everything to the left of any node is less than or equal to that node. Anything to the right of any node is greater than that node. Now, what this implies then is this entire thing is a binary tree. Isn't this guy a binary tree as well? Isn't he effectively the root node of a binary tree? And isn't this guy the root node of a very, very sad binary tree? Need some water, I guess is the punchline. Okay, so we want to start looking at binary trees. So let's go in here, create a new project. And we'll just do a binary tree one initially. Okay. So I'll go into my Java. We're going to go ahead and we're going to create our class for our node. All right, and just like before, and we're creating a tree of numbers in this case. So just like before, we have a private int payload. Now, when we were dealing with linear linked data structures, we always had next node. We only cared about the next guy in the tree. In this case, though, we're not caring just about the next guy. We care about potentially the next, well, 2 children, right? So we're going to have a private node left child and a private node right child. Create our constructor for this guy, public node. This guy will take in an int payload. We'll set this dot payload equal to that. We'll set this dot left child initially to null, this dot right child initially to null. So that's the generic version of a node. All right. We want to go ahead and give ourselves a getter for payload, and then getters and setters for left and right child. Okay. Huh? This is the node. We haven't written our binary tree yet. Yeah, nodes don't know about roots. Nodes don't know about roots. I'm actually, because of the way I want to write this, I'm going to just give myself getters for left, for everything. Give myself getters for everything. So I'll go ahead and generate getters for all of those dudes. So there's my getters for them. So that's a read only. Okay? Now, we presume that at some point we're going to want to set a left or right child, correct? The way we're going to do this is actually internally within the node class, and you'll see how that's going to work here in a few minutes. All right, so now we want to create our binary tree. Class. All right, and this guy is going to have a private node root. Public binary tree. This dot root is equal to null. All right, so initially we have the empty tree. And let's go ahead and give ourselves a display for this guy right now. So we'll create a public void display. If this dot root is equal to null, system.out.println empty tree. Else, the nightmare begins. Okay, so in any case, we need to have the ability to add something to the tree. And we're always adding it at the root. So we're dropping it onto the root and then letting it kind of plinko down to wherever it ultimately needs to go. So we're going to have a public void add. Well, we'll add the payload. So this guy will take in an int payload. All right. So we'll deal with the trivial case first. Trivial case says if this dot root is equal to null, then we'll say this dot root is equal to a new node built with my payload. Easy enough, right? All right. Otherwise, if there is something already in the tree, in this case a root node, to add this guy, I need to determine whether he goes to the left or to the right of that root node. I kind of have two choices here. One choice is I can traverse the tree externally here. Okay, and we'll kind of write it both ways so we can see how this works. Let's actually let me decide which way I want to do it first, based on the homework I want to give you. Let's traverse it externally first, which means I'm going to have to give myself setters for the right and left. So let me generate setters for left and right child. So now I can set those for nodes. in binary tree here then, we need to find out where is a good home for this guy. So just like traversing a linked list, we kind of have our cur node, right? We're going to start off at the top of the list, top of the tree. So I'll say node cur node is equal to this dot root. So now we want to ask ourselves the question, is the value we're trying to add, payload, should it come to the left or to the right of cur node? Okay, so just for the sake of argument right now, I'm going to throw this in an infinite loop. So while true, we're just going to do this forever, and then you'll see how we'll get out here in a few minutes. I want to finally try to place this guy. All right, so while true, I'm going to ask myself, and I'm only in here if I have if I know there's at least a root node. So I'm going to ask the question, if payload is less than or equal to cur node dot get payload, then that means it's going to go to the left, correct? So we'll say cur node is equal to cur node dot get left child. He'll move to his own left. Else, cur node is equal to cur node dot get right child. All right, so we'll move ourselves into the correct place where we might be able to place something. That make sense? Now, we have to decide, do we place before or after this? So before we just move cur node, if we know this guy should go to the left, I need to ask myself a question. If cur node dot get left child is equal to null, I have a place I can put him. So I'll set cur node dot set left child equal to a new node built with my payload. If I didn't have a place for him to the left, that's when I'll have to traverse my tree to go down farther to look. So if I'm in here, I already have a root node, so I'm going to try to place them. So I'm just putting this inside of an infinite loop for right now. If the payload should go to the left of the current node, I'll see if I can find him a home right away. Does the current node have a left child? If he doesn't, I found a place to put this guy. But if he does already have a left child, then we're going to go ahead and say, make cur node become his own left node, so the next time through this loop, we can try to place him again. Same thing here. If cur node dot get right child is equal to null, that means we have a place to place him to the right. So we'll say cur node dot set right child equal to a new node built from our payload. Otherwise, let's jump down the tree a little bit and we'll try to place him on the next pass through this loop. Does that make sense what we're doing there? This says try to place him to the left. This says try to place him to the right. We either definitely place him in those two cases, or we move ourselves down the tree. Now, if we did get them placed here, we can go ahead and break out of our loop. So even though this loop looked like an infinite loop up here, we actually broke out of that loop as soon as we were able to officially place them. Okay? Now, one thing we might do is if we want to kind of test this to see where he ultimately got placed, we could kind of build up a string. that kind of just we keep tacking on a left, then a right, then a left, kind of almost like GPS directions, right? Turn left at the first node, turn right at the next node, and that kind of thing to kind of get him into his final location. So maybe we say up here, we create a string directions, start this guy off at the empty string. If we are able to place him right at the top, then we'll say directions is equal to top or root. Otherwise, as we are going through here, if we are placing him to the left, we will say left. And I'll put a little space there at the end so we have some spacing. If we are placing him at the right, we'll put a right there for a little spacing. Just to show us where it ends up in there, because it's hard for us to actually display what a tree looks like. So in the end, after we place something, like this guy would be right then left. That'll tell us that he ended up in the right place. So we kind of know that we ultimately put him where he was supposed to go. All right, so let's go ahead and we can test this guy. So if we add a 4 initially, so when we add the 2 initially, that's going to go top. Let's go out into our main activity. We'll create an instance of our binary tree. Okay, and we'll say bt.add, and we added a 2, right? So we expect that guy to give us a top. Then let's try to add this 4. So 4 is not less than or equal to, so it's going to be greater than, so we expect this to be right. Now let's actually add we'll add another 4. So that's going to go right, then left. Should be where the next 4 goes, right? That's what that one should look like, right, then left. And then for this 2, this guy should go to the left. All right, and let's add a couple other small ones. Oop. So we do another 2, that's going to be left, left. And then if we add a, we add a 1, this guy will go left, then right. It is. Thank you. It'll go left, then it'll go left, then it'll go left. I really needed to make these a little bit bigger in order to get us a bigger one, but that's fine. Left, left, left. Okay. Let's make sure we are displaying after our loop is over. Let's go ahead and do a system.out.println directions. So we know ultimately where it showed up. And here, just so we can more easily pick it out, I'll throw some asterisks before that so it stands out in our logcat. Okay, so we'll go ahead and run this guy. There's not going to be anything to our interface. Our interface will still say hello world. Let's open up our logcat and go back to main activity. So we were expecting a, oh, hold on. I did it inside of the, I printed this out inside of the else, so that's why we never got the root displayed. That's fine. We'll check it as is. So that's why top. This actually should have said root, but whatever. All right, so otherwise we have right. This guy is not building up like I expected him to. Directions equal directions plus left. So here, we'll move this outside of there for right now. Oh, it's still in the else. I need to move it here. That's actually handy. It shows you where you are in, it shows you that that's the closing curly brace for that else, no matter how high up there that is. That's relatively new in this. All right, so why aren't I building my thing correctly here? Start at the top, while true. If it should go to the left, if I'm able to add it to the left, we'll go ahead and set it there. Update our directions to say left and break. Oh, that makes some sense. I need to be updating my directions here as I go along, regardless. So when I actually turn to the left, I need to go ahead and turn to the left. So I turn to the right, I need to go ahead and turn to the right. Because this is really where it's getting built up with multiple things. I was just tacking on the very last move, which I think looked accurate. This should be a little bit better this time. All right, so we should have root first, then we should have right, then we should have right left, then we should have left, then we should have left left, and then we should have left left left. So feels like those guys are getting placed in the right places. Okay, so now let's assume, well, minimize this here. Would you say that, not that this was incredibly, incredibly difficult, but would you say that this was maybe a little bit of a complexy looking solution? Almost like we're scaling the outside of the building. Kind of know what I'm saying? If we treat our tree, well, you know, if you treat the tree like it's a skyscraper or something like that, or even if you treat it as a tree, I guess it doesn't really matter. But it seems unsafe potentially for us to be hanging from the outside of this building, say, okay, I need to go to the left. So you grip down to the left and you swing down there. Not that it didn't work, and not that it's even bad code. Although typically, I would say if you were, were given a true-false question at some point, whether or not a infinite loop is ever a good idea, the answer would probably be no. That infinite loops are bad ideas. But we know we'll break out of this loop. So we wrote our logic such that it would make sense for us to break out of the loop. Realistically speaking, the alternative to this would have been to create an additional Boolean, whether or not this guy's been placed. So we would have taken up more memory to do this, and then also had to ask an additional question the next time up, while also having to ask an additional question each time through. So we would have had to ask a more complex question. Has the guy been placed? If no, try to place him. Has the guy been placed? If no, try to place him. So on and so forth. And then when we got down here and we finally placed him, we would have had to set the Boolean equal to true. He has finally been placed. Next time through the loop, he would finally fail. We drop past it. So it would actually take up some more memory, right? But it also might be a little bit easier to follow. So you choose. Otherwise, to somebody looking at this, it's like, okay, well, they've written an infinite loop. Let's hope they have an escape plan or something like that. So that's where we've given ourselves the escape. So you can kind of choose your poison there, I guess. But punchline with this is one accurate solution to adding something to a tree. But I'm going to suggest an alternative solution. Let's kind of clear the board here. And this is what we're going to implement for our homework, this alternative solution. So let's say I'm trying to add this 4. We get here, we see the top of the list is empty, or is not empty. Here, we'll add the 2 first. Top of the list is empty, it trivially gets added. Don't have to do anything special. Now we'll try to add the 4. Is the top of the tree empty? It's not. So what we're going to do is we're going to ask this node to add this new payload. So now it's 2's responsibility to place him. So instead of us climbing outside of this building, we're actually just passing the buck. We're saying, okay, well, I can't place it right here. And from a binary tree's perspective, the only variable I have to work with is root. Okay, so therefore, remember before I mentioned when I first wrote this that I wanted to have the setters turned off here for left and right, which means that you can only access left and right. Since they're private, where can we access left and right? While you're inside of the node class, right? So I'm going to go ahead and take these 2 guys out, which should make the current solution break. So if I try to run this right now, can't find set and left. Or set left and set right. So I'll leave it like that as our current state of things. All right, so what we're going to do here is we're going to actually pass the buck. We're going to say, 2, please try to add 4 to yourself. So 2 is going to receive that payload. And then now 2 is a node, right? So internally 2 is going to say, okay, where should this guy go? He should go to, he's greater than me, so he should go to my right. All right, so he's going to look down, he's going to say, do I have a right child? In his case, he doesn't, so he'll just go ahead and place it. So he'll set his right child to that guy. Then we try to add another 4. We're adding it to the binary tree. Binary tree says, root is already taken. Therefore, I'll just ask my root node to add this dude. So we pass the 4 to the 2. So now I'm the 2. I'm a node 2, and I have a 4. I need to place the 4. Should this go to my left or to my right? It should go to my right. I look down at my right child. I already have a right child. I can't place him, so what do? I hand him off to my right child. Place this guy. So now 4 is in charge of placing him. So 4 says, okay, where should this guy go? To my left or to my right? He should go to the left. So 4 looks down, sees that he has an opening for a left child, and he'll go ahead and adopt him and place him there. Then we have a 2 come into the system. Binary tree looks at root, says, already taken, so he hands the 2 off to his root node. 2 now has the 2 and says, okay, where should this guy go? He should go to my left. He looks down, he sees, oh, I have an opening. My left child is not currently occupied, so I'll go ahead and set my left child to that guy. Now a node can set his left child to another node because we're inside the node class, right? That's why we didn't have to have setters for those guys. Then we'll try to add the 2. We can't do it at the root node, so this guy gets access to it. He says, should this go to my left or my right? It should go to my left. He sees that left is already taken, so he hands this off to his left node. Now I'm the second version of 2. Should this go to my left or right? It should go to my left. I have an opening, so we place it on his left. Same thing with the 1. Pass the buck, pass the buck, pass the buck, place it. That makes sense? Now the one thing you'll have to do differently here though for your directions is you'll have to do a series of prints instead of println if you want it to all show up on one line, because we're not going to be able to build, you're not going to be able to conveniently build up this direction string here, because as you pass it from child to child, they'll have to print out, I was the left. That's just one stop along the road. So they're just going to build a left, then he'll print out a right, then he'll print out a left as we're kind of going through things. Make sense? All right, so for Thursday, implement add in the other way, the node internal way that we just described. Sound good? You'll be making a majority, you'll be gutting most of this, and you'll be making a majority. Maybe you should write like an add to, a second version of add, so you have both of them. But you'll be making a majority of your changes in the node class. And it will actually, you'll notice that it's actually be a lot less code, because each one's just going to have a this statement in it. If I can place them, place them. Otherwise, pass the buck. Make sense? All right. Today, faculty, student, staff Bible study, God and Grub. Go to the cafeteria, sign in, grab your tray, take it down to the terrace room. That's from noon to 1.